All right, welcome everyone. Think of this as a whirlwind tour of the programmer's toolkit. We're going to open it up and look at the fundamental puzzles and concepts that are really the building blocks for all the software you use every single day. You see, this isn't just about writing code. It's about learning a new way to think. So let's get right into it.
So think about this for a second. What on earth could possibly connect your favorite video game, the sequencing of our own DNA, and these massive databases that run the world? Well, the answer is algorithms. They are the secret recipes, right? The elegant step-by-step instructions that tell computers exactly how to solve problems, whether that's drawing a character on screen, analyzing a gene, or finding one tiny piece of data in a sea of information.
So here's our game plan. We're going to start with the absolute basics, how to think like a programmer by solving some simple puzzles. Then we'll get into some core algorithms. These are the real powerhouses of computing. After that, we'll see why organizing your data is just as important, tackle some seriously clever advanced puzzles, and finally, we'll put it all together in your new programming toolkit.
All right, Section 1, Puzzles, Problems, and Code. This is where it all begins. At its heart, programming is just about looking at a challenge, any challenge, and breaking it down into a series of logical steps that are so clear, so precise, that a machine can follow them perfectly every single time. Let's kick things off with a puzzle you definitely already know the answer to: leap years. You know one when you see one, right? But here's the real question. Could you write down the exact rules for what makes a leap year? Because that right there, that's the first step in programming, turning that knowledge you have in your head into a set of precise conditions a computer can actually understand and follow. And here is that exact logic translated into a bit of Python code. Now, let's just look at that if statement for a second. That little percent sign, percent, is something we call the modulo operator. It just gives you the remainder after a division. So year %4 equals 0 is just a fancy way of asking, is the year perfectly divisible by 4? The code checks two big conditions. First, is the year divisible by 4 and not divisible by 100, or is it divisible by 400? If either one of those things is true, we've got a leap year. See, it's just pure, simple logic. And boom, here's the proof. We give the program an input, in this case the year 2000. It runs that logic we just talked about, and out comes a clear, correct answer. This simple little loop, input, process, output, that's the fundamental heartbeat of pretty much all programming. Okay, let's level up. On to Section 2, Core Algorithms. Now that we have the basics of logical thinking down, we can start looking at some simple but incredibly powerful algorithms that let us find some really fascinating patterns hidden in data. So check this out. It's a really beautiful mathematical curiosity called Amicable Numbers. The rule is pretty straightforward. You take a number, say 220, and you find all of its proper divisors. That's just every number that divides into it evenly except for the number itself. You add all those up, and for 220, you get 284. Now here's the magic. If you do the exact same thing for 284, you get 220. They have this perfect reciprocal relationship. And of course, we can write a program to hunt for these. When we feed it 220, the code just churns through all the numbers from 1 up to 219, checks for divisibility, adds them up to get 284, and then it does the whole process again for 284 to get back to 220. It confirms the relationship, acting like a little digital detective finding these hidden mathematical gems. Now, for a classic problem that has huge real-world implications, the Maximum Subarray problem. So imagine you have a list of numbers, some positive, some negative. Your job is to find the one connected slice of that list that has the largest possible sum. Now, you could try checking every single possible combination, but for a big list, that would take forever. Luckily, there's a much more elegant and lightning-fast solution called Kadane's algorithm. Let's just watch it in action. With this input list, Kadane's algorithm is smart. It only needs to scan through the list one time. It keeps track of the best sum it's seen so far and the current sum of the slice it's on. It sees the 2, 3, 4 and thinks, okay, that's a sum of 9. That's my new record. Then it gets to the -3 and realizes adding it would actually make the sum go down. So it knows that great segment must have just ended. It's incredibly fast and accurate. And why does any of this matter? I mean, who cares about sums of numbers in a list? Well, it turns out this exact algorithm is used in computer vision to find the brightest block of pixels in a picture. And even more amazing, it's used in genomic sequence analysis to find the most biologically important segments inside a strand of DNA. That's a pretty powerful application. This brings us to a really crucial idea. To solve the bigger, more complicated problems, just having clever algorithms isn't quite enough. We need smart ways to organize and store and access our information. This is where data structures come into play. The algorithm is the recipe, sure, but the data structure is how you organize your ingredients.
One of the most fundamental data structures is the linked list. Honestly, the best way to think of it is like a scavenger hunt. Each clue in the hunt, we call it a node, holds a piece of data. But critically, it also holds a pointer, which is really just the location of the next node in the chain. It creates this dynamic chain where each item tells you exactly where to go to find the next one.
Okay, let's look at two other key structures you'll see everywhere: a queue and a stack. A queue is super intuitive. It works on a first-in, first-out principle. We call it FIFO. It's exactly like a line at the grocery store. The first person to get in line is the first person to get served. Now, a stack is the complete opposite. It's last in, first out, or LIFO. Think of a stack of plates. You always take the one off the top, which was the last one you put on.
And trust me, queues are absolutely everywhere in computing, even if you can't see them. They're used to explore networks and trees one level at a time. They help your computer's CPU manage its massive to-do list of tasks, and they act as buffers to make sure data doesn't get lost when it's streaming in really fast. They're kind of the unsung heroes of keeping systems stable.
All right, let's head into our final set of problems. This is kind of the boss level, where we combine everything we've learned, our algorithms and our data structures, to solve some really ingenious and complex challenges.
Okay, here it is. Every programmer's worst nightmare. A program that gets stuck running in circles forever. An infinite loop can crash the server, freeze an application. It's a huge problem. So the question is, how can you write code to detect if you're stuck in one of these cycles?
The solution is just so clever and elegant. It's called Floyd's cycle-finding algorithm, but it's better known as the tortoise and the hare algorithm. Imagine two pointers moving through your data, like two runners on a track. The tortoise moves forward one step at a time. The hare, though, moves two steps at a time. Now, if there's no loop, the hare just gets to the end first, no big deal. But if there is a loop, the hare, moving faster, is guaranteed to eventually lap the tortoise. The moment they land on the same spot, you know you found a cycle. Brilliant.
And for our grand finale, a famous, kind of grim but fascinating thought experiment, the Josephus Problem. Here's the setup. You have n people standing in a circle. You go around the circle and eliminate every kth person. The big question is, if you want to be the last person standing, where in the circle should you position yourself?
Let's just walk through this example nice and slow. We've got 7 people, and we're getting rid of every third person. So we start counting. 1, 2, 3. Person 3 is out. The circle shrinks. We pick up from person 4 and count again. 4, 5, 6. Person 6 is out. This just keeps going, with the circle getting smaller and smaller until only one survivor is left. This problem is a perfect use case for a special kind of data structure called a circular linked list, where the very last element points right back to the beginning, perfectly mimicking that circle.
So, let's take a step back and ramp all this up. We've covered a lot of ground today, but every single concept we've touched on is an essential tool that every programmer, or aspiring programmer, really needs to have in their toolkit.
So what did we actually put in our toolkit today? Well, we started with simple, pure logic, like the leap year problem. Then we added some efficient searching with Kadane's algorithm. We learned how to organize our data with things like linked lists and queues. And finally, we combined all of that to solve really advanced puzzles like Floyd's cycle finding and the Josephus problem. You can see how each tool builds right on top of the last one.
Look, these puzzles and data structures, they aren't just academic exercises or something for a test. They are the fundamental building blocks, the logic, the structures, and the creative solutions that engineers use to build the entire digital world we live in right now. The only question left is, what are you going to build with them?